Okay. So we are very excited to have Nutan Limaye speaking at the TCS Plus seminar this week. She just joined IT University of Copenhagen in Denmark. Before this, she was a professor at IIT Bombay in India for 11 years. She has done seminal work in circuit complexity, and today we will hear about a breakthrough result in algebraic complexity. Thanks for agreeing to talk here, Nutan, and please take it away from here. I think you're muted.
Thanks, Omega, for the introduction. Thank you, everyone, for coming. I'll be talking about superpolynomial lower bounds against low-depth algebraic circuits. This is a result with Shrikant and Sebastian. So I've planned the talk in the following way. I'll start with a brief introduction to algebraic circuits. I'll talk about why one would want to prove lower bounds for constant depth circuits. Then I'll state our result. And our lower bound result actually implies a couple of other results, so I'll state those as well. I'll try to present a few proof ideas. I'll probably not be able to go deep into any of them, but maybe I'll just give the flavor of the proof ideas. And I'll end with some summary and open questions. And perhaps if there are more questions and more interaction, it's okay to sort of not do some of these bullet points. So we will see how it goes. All right. So a polynomial P, we'll assume is over n variables throughout and over an arbitrary field. If the field is, say, a specific one with some restrictions, I'll mention it. To compute polynomials, one can consider many models of computation, and algebraic circuits is one such model of computation. So quite a simple enough model to describe. It is a directed acyclic graph. Its leaves are labeled with variables or field constants, and intermediate nodes are labeled with operators like plus and multiply. A plus gate just adds its inputs. The multiplication gate multiplies its inputs, and then there is a designated output node that computes the final polynomial. We can assume without loss of generality that these circuits are layered, a plus layer followed by a multiplication layer followed by a plus layer and so on. It is okay to assume this without loss of generality because if there were consecutive layers, you can just merge them. It's also okay to assume without loss of generality that the top layer is a plus gate, because if not, we can just add a trivial plus gate at the top. For a circuit, we consider a couple of parameters which kind of describe the complexity of this circuit. One such parameter is the depth. The depth of the circuit is simply the length of the longest leaf to output path. And for a layered circuit, it's quite easy to describe. For example, here, the depth is 3. And such circuits we'll also refer to as sigma pi sigma circuits to indicate that the top is plus, then is a multiply, and then a plus. One other parameter of interest would be the size of the circuit, which is the number of operators in the circuit. In this case, one could count, it's, I think, 8. Okay, so these are algebraic circuits, and they compute polynomials. This is the model of computation of interest to us in this talk. Algebraic complexity theory is the area where you study polynomials, computation of polynomials. So for instance, let's consider this very simple polynomial. It just sums, it's just a summation over all possible subsets of variables coming, all possible subsets of the universe n. And for every subset, we add a monomial to this polynomial, which is essentially the multiplication of the variables indexed by this set. It's not very difficult to see that computing this polynomial can be done using 2 to the n operations. But of course, the same polynomial can also be computed in a slightly different way, as follows. And over here, the circuit is depth 3 with a trivial plus gate at the top, which I have not drawn here, then a multiplication gate and a plus gate. And you can observe that, in fact, the same polynomial is being computed by this operation as well, and it uses far fewer operations. So in general, this is a very simple example, of course, but given a polynomial, you could ask, how many operations are necessary and sufficient to compute this polynomial? And for certain polynomials, we would like to show that very few operations do not suffice. This kind of statement would be a lower bound statement, to say that there are these polynomials which require a lot of operations for computation. So one would wonder why one wants to prove such statements. Why would I want to prove low bound statements for algebraic computation? Or for that matter, any computation? Why would we want to prove lower bounds? And one possible reason, which is perhaps quite convincing, is that it is a dual to algorithm design. So algorithm design is a very natural computational problem for any computational task we want to execute. And say for a certain task, after much effort, there is no efficient algorithm, or one can't do better than what is known presently. Then it's probably useful to sit back and think as to why we are not able to make progress beyond a certain point. And that's where the thinking behind coming up with low bounds comes into the picture. So low bound thought process is sort of a dual to algorithm design. Specifically in the algebraic world, it is known to help lower bounds in the Boolean world. So in the Boolean world, the P versus NP question is quite an important central complexity question. And it is known that if P versus NP question can be resolved in the negative, then its algebraic variant also will be resolved in the negative, which is to say that proving algebraic circuit lower bounds is sort of a stepping stone, perhaps, towards proving resolving the P versus NP question in the negative. So, and this is kind of a formal statement proved by Bergesser that if you can prove lower bounds, that algebraic circuit lower bounds are a stepping stone towards proving Boolean circuit lower bounds in some non-uniform universes. So, therefore, proving lower bounds in the algebraic setting becomes an interesting question. The next question would be, why prove lower bounds for constant depth circuits? And here the story is actually quite different from the story in the Boolean world. In the Boolean world, what's known is that there are quite simple Boolean functions that cannot be computed by constant depth Boolean circuits. Whereas the picture is very different in the algebraic world. What's known, for instance, one of the statements that's known is that suppose you have a polynomial P on n variables of degree D that is being computed by polynomial-sized circuit. Say the circuit has size polynomial in the two parameters we are considering, n and d. Then it's known that in fact P's computation can be squeezed down to just depth 4, sigma pi circuit of not too large size. The size of such a computation turns out to be n to the order square root d. The trivial upper bound would be n to the order d, but the statement tells us, which is something non-trivial, that is, you can actually just do the same computation using only n to the order square root d operations. So this result was proved by Agrawal Vinay, Corin, and Sebastian Tavenas. And in fact, something more is known about constant depth circuits. Not only can we squish the circuit down to depth 4, we can even squish it down to depth 3 without extra blow up. This statement is true only over characteristic 0 fields, but well, you can go down from arbitrary depth polynomial-sized circuits down all the way to depth 3. What these depth reduction results tell us? So this result was by Gupta, Kamath, Kayal, Saptarshi, and Sebastian. So what these results tell us is that constant depth circuits are quite powerful. So proving lower bounds for constant depth circuits would, in certain parameter regime, even give general lower bounds. So in that sense, proving lower bounds for constant depth circuits is an interesting question. Another way to think about the lower bound question for constant depth circuits is from the lens of VP versus VNP question. So VP and VNP can be thought of as algebraic variants of P and NP. And as I said, separating these two classes is considered to be a stepping stone, perhaps, towards separating P and NP. So from the result that I just mentioned, we know that any polynomial that is in VP can be converted into depth 3 circuit of this size n to the order square root d. And the following statement, which is of course not known, it is still open, but suppose somebody is able to show that there is a polynomial in VNP such that any depth 3 circuit for it requires size strictly more than n to the omega square root d. So it requires size n to the little omega square root d. If we are able to prove a statement like this, we would in fact separate VP from VNP. So basically what I just tried to say through all this was that proving lower bounds in the algebraic setting is interesting, and proving constant depth lower bounds also is quite interesting. Okay. All right. So now that I've said that proving lower bounds for constant depth circuits is interesting, the next obvious question is, so what's known? What's known in terms of lower bounds for constant depth circuits? And here the picture is sort of not so rosy. Just to contrast it with the Boolean circuit complexity world, in the Boolean circuit complexity, in fact, quite a lot is known for several decades now. In the 80s, through a series of really beautiful results, it was shown that really strong exponential lower bounds hold for constant depth Boolean circuits. Okay. But unfortunately, in the algebraic world, that was not known to be true. Such a statement, such strong lower bounds are still not known. So prior to our work, let me just tell you what was known before our work. So let's start with the very simple model of depth 2 circuits. This is just sum of monomials. Now in this model, of course, lower bounds are quite easy to prove because suppose I have a polynomial with k monomials, then it must, so its sigma pi representation must have size at least k. So for example, the very first polynomial we saw in the example on the second slide has 2 to the n monomials. So if I were to represent it using sigma pi depth 2 circuits, then it will require size 2 to the n. So for very simple polynomials, an exponential lower bound is known if the model of computation is sigma pi. But what about the next level of difficulty? So what about sigma pi sigma circuits? Now, if I ask the same question for sigma pi sigma circuits, that very little was known. By this result by Kayal, Saha, and Sebastian, almost cubic lower bounds were known for sigma pi sigma circuits. And due to a more recent result of Gupta, Saha, and Tanki, for depth 4 circuits, n to the 2.5 lower bound was known. If you ask the same question for constant but larger than 5 depths, then in fact only superlinear lower bounds were known by these works. This is Shoup and Smolensky and Raz. Okay. So overall, no superpolynomial low bounds were known for even sigma pi sigma circuits. Okay. So if there are any questions, I'm not able to kind of read the room, but if there are any questions, please feel free to ask. All right. So then, what do we show? So we give the first superpolynomial low bound for constant depth algebraic circuits. So that's the main result. Just to elaborate, let n, d, and delta be some growing parameters, and let d be the dependence on d between d and n is as given. We also work over characteristic zero fields, so our result holds over characteristic zero. For now, we do not know how to do it for all characteristic, but it holds for characteristic zero. What we show is that there is an explicit polynomial of degree d such that any algebraic circuit of depth delta, computing it, must have size n to the d to the inverse exponential in delta. So the important thing here is that d is in the exponent of n, and of course the bound deteriorates with delta. Unfortunately, it deteriorates inverse exponentially with delta. One could expect it to deteriorate inverse linearly with delta even, but we don't know how to prove that right now. What we get is an n to the d to the inverse exponential lower bound. Okay, so that's the main result basically. So this is the lower bound result. I can make that explicit polynomial quite explicit. So it is indeed a very well studied polynomial called the iterated matrix multiplication polynomial. It's a very easy to describe polynomial. You have D matrices. Each matrix is n cross n. And you have fresh set of variables per matrix. So you have n square variables, another fresh n square variables, totally n square times D variables. And we think of this as ijth entry being x1, ij, etc. And now the polynomial we are interested in is the 1, 1th entry of the matrix obtained by multiplying all these matrices. So that's the IMM polynomial. It's a very natural polynomial that encapsulates, for example, reachability in the Boolean world. It is a generalization of matrix multiplication and so on. So it's a very natural polynomial that is well studied. So just to state our result in terms of IMM, we show that any algebraic circuit of depth delta computing IMM ND must have size n to the d to the inverse exponential in delta. And if we actually look at a specific delta, for example, at delta equal to 3, we get slightly tight bounds as well. So for example, at delta equal to 3, we are able to show that the lower bound is n to the omega square root d. And this is tight by the depth reduction result I mentioned earlier. Because any polynomial that is computable in VP, and IMM is one such polynomial, has depth 3 circuits of size n to the order square root d, and we show that that much is necessary. So at depth 3, we in fact get tight lower bounds for IMM. Right.
So I have a question. So you said, so we also know that there is an n to the order square root d size circuit for computing IM.
Yeah. Okay. Depth 3 circuit. Yes, exactly. Exactly. That is because of the depth reduction result I mentioned earlier. Yeah. Thanks. Okay, so that's the lower bound result. Just to put it back into the perspective of the VP versus VNP picture, we said that if we are able to get a polynomial f in VNP, for which we are able to prove something like a n to the little omega square root d lower bound, then we will separate VP from VNP. We don't quite get that. But we get a polynomial that is in VP. So of course, with our polynomial, we can't even hope to separate VP from VNP. That's one thing. Also, our lower bound is n to the omega square root t. So perhaps maybe with similar techniques for a harder polynomial, we may be able to get n to the omega square root t. It's a good question to think about, but as of now, this is what we have. All right. Our lower bound result also gives a few interesting, implies a few interesting results. One of the results is about polynomial identity testing problem. So let me just tell you what that problem is. It's an important problem studied in algebraic complexity theory. So what you're given is a black box access to a polynomial. What that means is you're not given the polynomial in its sum of monomials form, but you get to query this polynomial, evaluate this polynomial at a point of your choice or at points of your choice. And then after querying the polynomial at as few positions, as few points as possible, you want to determine whether the polynomial is identically 0 or not. Okay. And there is a very simple randomized polynomial time algorithm to do this. Just query the polynomial at a random point. Yeah? By Schwarz-Zippel, or it's also known as Schwarz-Zippel, Lipton, de Mello lemma. It's known that by querying at a random point with really good probability, you can determine whether the polynomial is non-zero or not. Okay, and maybe you have to repeat it a few times to improve your error probability, but it's doable. And people have tried to understand whether this very simple randomized algorithm can be de-randomized efficiently. So the de-randomization of polynomial identity testing question has been studied for quite some time now. One interesting statement about it that connects it to lower bounds is by Cabanets and Impalkle also. Of course, they prove other interesting things as well, but the most interesting one for our purpose is this one. What Cabanets and Impalkle say is that if you're able to separate VP from VNP, then in fact, you will also get sub-exponential deterministic algorithms for PIT, for general circuits. So if you're able to show that there is a polynomial that cannot be computed by polynomial-sized circuits, then PIT becomes easy. There is a sub-exponential time deterministic PIT algorithm for general circuits. Now, this result by Cabanets and Pagliazzo has been extended in many different ways. In algebraic complexity, one result which kind of is useful for us is the following. There is suppose one can come up with an explicit small degree polynomial hard for constant depth circuits. So instead of hard for VP general circuits, if we are able to come up with a small degree polynomial hard for constant depth circuits, then it implies deterministic sub-exponential time algorithms for constant depth PIT. So basically what this means is that a similar implication as in Cabanets and Pagliazzo, but with an assumption about hardness against small depth circuits. And this is a result by Chow, Kumar, and Solomon. So basically, if you put together the lower bound we have in the paper with this result that says that lower bounds imply deterministic PIT, we get deterministic PIT. So that's really one of the result that is implied by this work of Chow, Kumar, and Solomon and our lower bound. So just to state it clearly, given black box access to constant depth polynomial-sized circuits, computing a polynomial P over characteristic 0, there is a deterministic algorithm that checks whether P is identically 0 or not. That is, it solves the PIT question that runs in time sub-exponential time. Okay, so it just comes from the previous result I mentioned and our lower bound. What was known for PIT before this? So a lot of work has gone into coming up with deterministic PIT algorithms. Even for constant depth circuits, um, there is a lot of work in the last 2 decades. And as far as I know, in the black box regime, where you do not get access to the circuit itself, but only you get to query the circuit, the best known result for depth 3 is this. Um, it says that if you have a depth 3 circuit, sigma pi sigma, with top fan in K, then for such circuits, PIT can be solved in time n to the order K. This is a result by Saxena and Sheshadri from 2012. So just imagine if K is like n, which it can be, then they get n to the n running time, which is, I mean, you would much rather just brute force. So this doesn't give anything very interesting. In that regime where there is no bound on K, we still get sub-exponential time algorithms. But on the other hand, suppose K is small, say K is order 1, then they actually get deterministic polynomial time algorithms for PIT for such circuits, whereas we do not get anything better. We still continue to get sub-exponential time algorithms. So sort of our result is incomparable depending on the value of K, but this is the best known that we have, as far as I know. And as I already said, our result is essentially implied by the result of CKS with when combined with Aloha. Their result builds on Cabanets and Pagliazzo and a work of Dvir, Shpilka, and Yodev. So that's what we have for polynomial identity testing. Yet another result that we get through a lower bound as a byproduct of a lower bound with a little more work is depth hierarchy theorem. So what we are able to show is that over characteristic 0 for every constant gamma and growing parameter s, there is a polynomial that is computable by depth gamma size S circuits, which for which if I only allow depth gamma minus 1, then the circuit has to be of size strictly more than s to the omega 1. Yeah, so basically this summarizes all the results we have. So I told you about the low bound result. Low bound combined with the previous machinery for hardness versus randomness gives PIT result. And we need to come up with a polynomial Q gamma that is specially designed to work for this result, but it follows from the techniques we have in the paper already. Okay, so these are the set of results we have.
So for the hardness versus randomness result, do you need? So why do you need that? Why do you need that it should be a low degree polynomial that is not computable by constant depth circuits?
Right. So our result, our lower bound is for low degree. So our lower bound only holds in the low degree regime, and therefore, in order to get anything, the statement for the hardness versus randomness statement should be such that our result is usable. So our result currently holds for small degrees. So if, say, for instance, we use the previous result, there was a result before this CKS by Dvish, Pilka, and Yodaya that said that if you can come up with a polynomial that is hard for constant depth circuits, then you get sub-exponential time PIT for constant depth circuits. But that result we were not able to use for our purposes. But it so turned out that CKS already has that Dvish Pilka Yahudev result specialized for small degree case. And then we were just able to use it, right, just from their paper. Yeah.
Nice. Thank you.
Yeah. There are other questions maybe, or else I can go ahead. So let me carry on. So as I said, the crux of the work is in proving this lower bound. So for the rest of the few minutes that I'll talk, I'll primarily focus on this one. All right. So let me just give you a little bit of the proof outline now. One of the main proof ingredients is this idea of escalation. So escalation probably has been used in many ways in the literature. So let me just tell you what I mean by it right now. So what we were able to do was we were able to say that if you have lower bounds for weak models of circuits, some sort of weak models of circuits, then we can lift those lower bounds for general circuits. So we were able to prove this sort of a statement, and then we were also able to get these lower bounds for weak models of circuit. So this is how the proof proceeds. We get a lower bound for a weaker model of circuits, and then we are able to prove separately that that already implies general circuit lower bounds. Okay, so that's kind of the main idea. In order to tell you what these weak models of circuits are, let me just tell you a couple of restrictions on classes of polynomials. So we'll talk about three different types: homogeneous, multilinear, and set multilinear. A polynomial is homogeneous if every monomial in it has the same degree. A polynomial is multilinear if every monomial has at most one occurrence of any variable. And suppose I divide the set of variables into set x1, x2, etc. up to xd. Then a polynomial is said to be set multilinear with respect to this partition if every monomial has exactly one variable from each set. So just as an example, the IMM polynomial that I talked about is a set multilinear polynomial because it uses exactly one variable per matrix. And the matrices were basically sets of variables. So IMM is one such example. There are many other natural examples. And set multilinear model of computation has been considered again for the last couple of decades, quite a bit, more than a couple of decades now. Corresponding to these classes of polynomials, one could define classes of models of computation. So I'll define circuits. A circuit is homogeneous if every gate inside it computes a homogeneous polynomial. It's defined quite naturally. It's multilinear if every circuit is defined, every gate in it is multilinear. It computes a multilinear polynomial. And it is set multilinear if every gate in the circuit computes a set multilinear polynomial with respect to a subset of variables. All right. So with these definitions, now I'm able to tell you what I mean by escalation. So in order to do that, let me recall an older result by Raz from 2009. This is to say that, escalation is not something we invented or something. Such results are known widely in many areas of complexity theory, and in particular also in algebraic complexity theory. So these results often come because you are able to do efficient conversion of models of computation. For example, suppose I have a formula of size S computing P. A formula is basically just a circuit where the underlying graph is a tree. So suppose I have a formula of size S computing a polynomial P. What Raj showed was that you can convert it into a set multilinear formula. As long as P itself is a set multilinear polynomial, then the formula computing it can be made set multilinear. And it can be done without too much blow up in size. So S becomes poly S. Well, if it just became poly S, that would be ideal, but it's not quite that. You still have some polylog factors in S that come and hit you. Okay, so his conversion took a formula of size S and resulted into a set multilinear formula of this slightly extra size. Now, if we substitute a specific value of D in the previous conversion, let's say I take D to be log n by log n, and I also say that the formula to start with was polynomial sized, then what Raz's result tells you is that the set multilinear formula that you obtain is also of polynomial size. So you start with a polynomial size formula and then you result into another polynomial size formula. Now, escalation is implied by the contrapositive of the statement. If I'm able to show a superpolynomial lower bound, an n to the omega d type lower bound for set multilinear formulas, then I get superpolynomial lower bound for general formulas. So this setup of escalation was already present in the literature and in many other forms as well. This is just an example. This specific result we couldn't have used because this transformation that RAS does not preserve depth. So it kind of increases the depth irrespective of the original size of depth of the formula. The resulting formula tends to have large depths. So this is not quite usable. There was another reason why these escalation kind of results were not useful. One big reason was, though there are many lower bounds known for set multilinear circuits, even constant depth set multilinear circuits, most of them were of this form. They were of the form some exponential quantity in D times poly n. However, the kind of escalation results that are known incur more blow up in the simulation from general formula to a specific type of formula. As a result, it is more fruitful to have lower bounds of the type n to the omega f of d, where the f of d is in the exponent of n. Because of the nature of this bound, we call these non-FPT lower bounds. Because FPT basically means the fixed parameter is multiplicatively hitting the quantity, but we want a non-FPT lower bound, which is that the function of d should be in the exponent of n. So such lower bounds were not known for larger depths prior to our work. So what we were able to do was that we were able to prove such a lower bound for set multilinear formulas of arbitrary depth. So what we were able to show was, if you look at only set multilinear circuits, computing IMM, then for any depth delta, as long as it's constant, say, the size of the circuit must be n to the d to the inverse exponential in delta. This quantity has been appearing again and again, so perhaps it's sort of familiar by now. So we get, in particular, we get the dependence of d in the exponent of n as required. A couple of things I would like to say about this lower bound. One thing is that if we look at depth 5, for set multilinear circuits at depth 5, so you have sigma pi, sigma pi, sigma set multilinear circuits. We in fact get the tight lower bound again in this case. So I'll tell you why that is tight, but we get a lower bound of n to the omega of square root d for depth equal to 5. Why this is tight is because there is a depth 4 implementation of IMM, which is just done by like Savage-like algorithm, divide and conquer type strategy, that gives a n to the order square root d upper bound for IMM. And what we are able to show is that even with depth 5, you still need n to the omega square root d. So at depth 5, our result is slightly stronger than what the general result is saying for arbitrary depth. That's one thing. And with our escalation result combined with this strong lower bound at depth 5, already at depth 3, we get the tight lower bound I was talking about. So even if we were not able to prove our lower bound for arbitrary depths, at depth 5, this result alone would have shown something which was not known before this, which is that n to the omega square root d lower bound for depth 3 circuits. Right. So this is one of the components in the proof, that we get a set multilinear lower bound for all depths which is non-FPT. That is, the dependence of d is in the exponent of n. Okay. The other component, as I said, is that of escalation. So let me mention a little bit, a couple of things about that as well. So what we were able to do is that we were able to do efficient conversion from general to set multilinear in 2 steps. First, we said that if you have a general circuit of size S and depth gamma, then such a computation can be converted into a homogeneous circuit of depth twice as much, so 2 gamma minus 1, something like twice as much, and with a blow up which is an FPT blow up. So S becomes poly S, and the factors that are exponential in D are sort of hitting poly S in multiplication. So this is an efficient conversion. Unfortunately, for this conversion to go through, we require characteristic 0. We do not know how to do this conversion from general circuits to homogeneous circuits, preserving the depth more or less without the characteristic 0 assumption. But then we convert the homogeneous circuit into set multilinear. This is the second step. And here actually we do not need any assumption on the characteristic. We are able to do this for any characteristic. In fact, here, while going from homogeneous to set multilinear, you don't even blow up the depth. The depth also stays as it is. Except the blow up in the size is a little more in this case. In the previous case, it was 2 to the order square root d while going from general to homogeneous. But from homogeneous to set multilinear, we do not know how to preserve this sort of a blow up. But still, the blow up is only multiplicative to poly S. It is of the order of d to the order d. So now that we have this efficient conversion, in contrapositive, obviously, it gives escalation. So let me just write it down. So what it says is that if we are able to give a non-FPT lower bound for depth 2 gamma minus 1 set multilinear circuits, then we get non-FPT lower bounds for the same depth homogeneous circuits. Moreover, such lower bounds, non-FPT lower bounds for homogeneous 2 gamma minus 1 depth circuits imply non-FPT superpolynomial lower bounds for general depth gamma circuits. So basically, proving very weak, or rather proving non-FPT lower bounds for a weaker model of computation gives superpolynomial lower bounds for general model of computation. So this is the kind of escalation idea that we were able to execute successfully. So just one slide summary of this is that proving weaker lower bounds can imply general lower bounds as well as PID. And so this is like the one slide summary of the entire paper, which is that you prove a lower bound for set multilinear circuits and then escalate. So this gives the entire result. So this is around 45 minutes. So maybe I'll just mention a few kind of summary and open questions. And I have a few slides later if some discussion comes up. Is that okay? So couple of, so here are a few open questions. One obvious open question from this work is, can we improve the lower bound? As I said, we have the dependence on, the dependence we have is n to the d to the inverse exponential in delta. And it's not, I mean, it's, I don't think that the dependence is kind of tight. For arbitrary depths, we could perhaps hope to get n to the d to the 1 by delta or inverse linear in delta. So this is absolutely not ruled out, perhaps quite desired. So for example, at depth 3, we have such a bound. We get n to the d to the half, so delta minus 1 or whatever. But for higher depths, we do not know how to show tight bounds. So we unfortunately have an inverse exponential delta dependence. Maybe another way to attack this question could be that just show that you cannot do better than this with these techniques. This technique we use has a bottleneck. So that could be another way to sort of answer this question. But yeah, that's something that's not clear. Yet another interesting question is, can we improve some parameters in the escalation statements? So as I said, there is this characteristic zero dependence when we convert general circuits to homogeneous circuits. And perhaps it's not essential. So that could be one question. That's just one example question. The other question could be that when I go from homogeneous to set multilinear, there is a blow up of d to the order d. And again, that is not clear why it should be d to the order d. Maybe we could do d to the, 2 to the order d, or 2 to the order square root d, or something like this. So maybe a couple of avenues to improve things there. Sumika was asking, this low bound implied PIT, and it kind of came ready-made from previous results in some sense. So PIT is one question that people think about in algebraic complexity world, but there are other related questions like the reconstruction question. Reconstruction question basically says that if you're given access to a black box access to a polynomial, by asking sufficiently many queries, can you come up with the circuit that computes that polynomial? So actually reconstruct the model that is computing that polynomial. And yeah, there are multiple ways of asking this question. But in the past, it has happened that if one is able to prove lower bounds for a model of computation, over the next few years, people were also able to come up with an efficient reconstruction for that model of computation. So this is a obvious next question one could try to attack. Another place where lower bounds from algebraic world have had some impact is so another area where these have turned out to be useful are algebraic proof systems. So here there are models of computations like read-once branching programs and so on, where low bounds are known, and these low bounds can be made functional, and functional low bounds give low bounds for algebraic proof systems. So I'm not very proficient with, or I'm not an expert in this area at all, but I know that low bounds in the algebraic world can imply a few things for algebraic proof system low bounds. And maybe there is something to be said about this low bound. Maybe one interesting question in this direction is, can we get functional low bounds for our model of computation? And I don't think our low bound is functional. One has to think about it. So that's also an interesting question. And finally, I did not get a chance to speak about the actual proof of the low bound for set multilinear circuits, but we use a sort of a measure which is similar to the measure used in the past. And maybe one other interesting question is to try to understand this measure a little better. I don't think we understand it. We got this low bound, but maybe there is something to be said about it. So yeah, this is the kind of questions which are of interest to me. And that's it. Thank you. Thank you for listening.
Thanks a lot, Nutan, for the great talk. Please unmute yourself to ask any questions.
I have a question. Where did you say that the n to the d to the 1 over the delta is the lower bound that you're hoping for? Is there no depth reduction of this form?
So I hope I got the question right. So are you asking why I would expect this lower bound?
Yes.
Okay. So this is because at least for IMM, we know that this upper bound holds. So for IMM, I would like to prove such a thing as tight. Another reason is that the depth reduction I mentioned, a version of that scales And maybe from that point of view as well, this is interesting. So it is possible, I think, that one could improve it. Certainly improving to anything better than inverse exponential is also interesting, I think. Right now we have n to the d to the inverse exponential, but even getting inverse quadratic would be a huge improvement to what we have. But perhaps for IMM, at least one should hope to prove n to the d to the 1 by delta, because there is such a upper bound as well.
For the escalation, is it known that we cannot improve the from size S to poly S? Do we need the factor of D there?
At least for certain depths, I can say that. So if you say that also the depth should not change, then it is known to be false. Because there are polynomials with for which there is a n to the omega d lower bound for depth 3 circuits. So if you also over and above say that the depth also shouldn't increase, then really that statement is just false. If you say that depth could increase by maybe a factor of 2 or so, then I'm not entirely sure.
So I'm wondering if I'm wondering if like this route can be taken to prove just lower bounds against algebraic circuits, like proving lower bounds against multilinear circuits implies, because if the depth is log n, then this does not give anything.
Yeah. So that's a good point, that if the depth is arbitrary, this is not giving you anything. And just to understand, so what you're saying is if I can get so escalation from multilinear to general circuits, say, this is what suppose is the goal. Then so again, that statement, I don't know how to make that statement work. I don't know whether there is a bottleneck that I can prove that, oh, such a statement shouldn't hold at all. So the efficient conversion question would be, given a general circuit, convert it into a multilinear one without increasing the depth, say, and not too much blow up in size. So it would be nice to prove such a statement. I don't know how to do it directly without, of course, set multilinear in particular is multilinear. So anything that is better than this, I don't know that. If you, okay, so the question, interesting question maybe is that if I don't want to go all the way to set multilinear, I just want to stop at multilinear, maybe we don't need to incur so much blow up. Of course, then proving lower bounds would become harder, because now we have to prove lower bounds for multilinear circuits. That's also kind of not quite clear. But yeah.
Okay, thank you.
How serious? So in the characteristic if the characteristic were non-zero, would you? I mean, how likely do you think that is for, say, infinite fields or of positive characteristic, for example? Maybe that might be the next.
Yeah. So actually, when I stated for characteristic 0, I should really be stating it in its most efficient way, which is actually it works for characteristic larger than D or something like this. So already the conversion only depends on, only needs that the field is characteristic more than D or something like this, poly in D, where D is the degree of the polynomial. So already it works there. What would be nice is completely remove the dependence on a characteristic. And I think this also should be doable. There is no real reason to believe that this is not doable.
Thanks.
But, yeah, we don't know how to do it. Yeah.
Maybe let's wait for a couple of minutes for more questions.
Seems to be something in the chat. Is this already?
Oh, it's mostly thank you.
Can you say anything about the techniques for getting this other form of the bounds? You know, this non-FPT style bound. What made the difference here?
Right. So previously, what was known was so Nisan and Wigderson in '95 showed this amazing lower bound for depth 3 set multilinear circuits. They gave, with respect to IMM, they were able to show that any set multilinear depth 3 circuit computing it must have size n to the omega d. So, you know, the best possible lower bound you can prove for set multilinear IMM computations. But there actually they use something known as partial derivative measure. This basically, some of you may already know this, but it essentially is the matrix obtained by, it's a rank of a matrix obtained by listing down monomials. So let me say it right. So it's a rank of a matrix which is obtained by so you have a set of variables. 1 to d is the index set, and I just partition it the way I like. And the partition gives rise to a set of monomials that depend only on one part and the other. And suppose I label the rows and columns using these monomials. Then I generate this matrix, and I fill this matrix up with the coefficients of the monomials obtained by taking the row and the column labels. So this is the measure. This is called the partial derivative measure. And for that measure, there is a well-known polynomial, which was also mentioned by Nisan and Wigderson, called the product of inner product polynomial. Now, this product of inner product polynomial actually is computable in depth 4 and has full rank. So already that shows that partial derivative measure is not going to give you the lower bound you want. Their example already shows this. So partial derivative measure was not going to be useful. For depth 4 lower bounds, actually, thanks to this result of a beautiful measure defined by Kayal in the last decade and used by a whole lot of people, we had set multilinear lower bounds for depth 4, up to depth 4. But that measure was very sensitive to the bottom gates being product gates. So we didn't know how to push that to even depth 5, like sigma pi, sigma pi, sigma. That was not quite clear. So what we were able to do was actually massage the partial derivative measure itself to get to the only thing we kind of changed conceptually was the set sizes. So if we partition the set into, you know, odd elements and even elements earlier, now we actually, the way we define the polynomial itself, the set sizes are slightly different. So we take that projection of IMM that results into smaller set sizes on one side, vaguely speaking. And just for entertainment, I have sorry about this, but yeah, a one slide summary of, yeah, but that's just a joke, yeah.
Thank you. This is great.
There is no dog in the talk. I think the talk is incomplete.
Okay, let's thank Nutan again for the great talk.
Thank you.